So far we have been considering unidirectional transport in one Cartesian coordinate system and a cylindrical, which is a curvilinear coordinate system. So, unidirectional transport, Cartesian coordinate system, coordinate perpendicular to a plane, okay, which means that surfaces of constant coordinate are planar surfaces, and we did a balance over a differential volume of height delta z in the z direction, and the unsteady conservation equation that we got was partial c by partial t is equal to minus partial j z by partial z plus s, j z is equal to minus d partial c by partial z, which means that partial c by partial t is equal to partial by partial z of d plus s, and if the diffusivity is a constant, then you get partial c by partial t is equal to d plus s. So, in this particular case, the surface area of opposing surfaces was the same, because all of them were planes. Curvilinear coordinates are used when you have objects with cylindrical symmetry, for example. Okay. So, for example, if I have a cylindrical object, okay, if I have a cylindrical object, if I wanted to express this in a Cartesian coordinate system, the surface would, for example, be x square plus y square, let me write this as the x coordinate and y and z. Okay. So, this will be of the form y square plus z square is equal to r square, which is inconvenient, it is not convenient. You would rather have the boundary surfaces as surfaces of constant coordinate. Okay. So, instead of this, we define the distance from the axis as the radial coordinate r, and use a cylindrical differential volume between two surfaces at r and r plus delta r to carry out the balance. And the equation has a slightly different form. Partial c by partial t is equal to minus 1 by r d by dr of r j r plus s. J r, flux in the r direction, is minus d partial c by partial r. Therefore, the conservation equation becomes partial c by partial t is equal to plus s, and if the diffusivity is a constant, partial c by partial t is equal to so that was the conservation equation. This is valid for mass conservation, energy conservation. Substitute temperature for concentration and thermal diffusivity for mass diffusivity. It is also valid for momentum conservation. Substitute the velocity for concentration, momentum diffusivity for mass diffusivity, except for velocity component that is around the axis. Okay, that if you have rotation of two concentric cylinders, for example, okay, the velocity in this direction is the velocity in the polar direction v phi. Okay. So, if I have two cylinders of different radii rotating with different velocities, the conservation equation for the fluid in between is different. Okay. I had written that for you. Partial v phi by partial t is equal to nu plus f phi by rho, and tau phi r. The stress also had a different form. Okay. Okay. So, those were the for rotating flow. And okay, and we had solved some problems, some steady state problems, both conduction as well as for the fluid flow rotating around the axis in the absence of any sources and for constant diffusivity. And we had also obtained expression for the heat transfer resistance, okay, for multiple resistances due to different cylinders of different thicknesses and different properties. Today we look at another coordinate system, spherical. Okay. This is used for objects of spherical symmetry, such as particles that are spherical in shape. The surface is a spherical surface, and if you place the origin at the center of the particle, the distance from the surface, from the center to the surface, is a constant. Okay. So, if you want a coordinate system where one of the coordinates is where the surface is a surface of constant coordinate, then one of the coordinates has to be the distance from the center. Okay. So, you have a spherical particle. Okay. If I take a general 3-dimensional coordinate system, x okay. If I have a spherical particle, okay, one of the coordinates has to be the distance from the center r. Okay. And that distance, the surface of the particle, okay, and the surface of the particle of radius r is going to be at r is equal to capital R. Okay. Okay. And the properties vary as a function of this distance from the origin. Okay. Unidirectional transport, that means that the properties depend only upon one coordinate. That coordinate is the distance from the origin. Okay. So, this is what is called a spherically symmetric system, that is, properties depend only upon distance from the origin and not on the orientation of the position vector. That is, I will get the same properties provided the distance from the origin is the same regardless of the orientation. Okay. So, these are spherically symmetric, okay, configurations. Okay. So, we have to determine the conservation equation for this, and then you solve that in order to determine the solutions at steady state and so on. Okay. So, let me go through the balance equation. Okay. So, I need to consider a differential volume between two surfaces of constant coordinate. In this case, the coordinate is the distance from the origin. Okay. So, okay, I need to consider two spherical surfaces, okay, one at distance r and the other at the distance r plus delta r. Okay. So, this volume is between two spherical shells, okay, the gap between two spherical shells, one of which is at r and the other is at r plus delta r. Okay. Okay. So, in this case as well as in the case of a cylindrical coordinate system, the surface area changes as r increases, as r changes. Okay. So, therefore, the surface area of surface at r is 4 pi r square. Okay. The surface area of the surface at r, spherical surface area, is 4 pi times the radius square. Okay. Surface area of surface at r plus delta r. This is equal to 4 pi into r plus delta r the whole square. Okay. And the volume is going to be equal to the surface area times the thickness of the shell. Okay, the volume is going to be equal to surface area times the thickness of the shell. Thickness is delta r. Okay. So, this is 4 pi r square delta r. Okay. And it is for this differential volume between two surfaces of constant coordinate at r and r plus delta r that we shall write down our mass conservation equation. Change in mass in differential volume. Okay, is equal to the change in concentration times the volume. Okay. C at r T plus delta T minus C at r T multiplied by the volume 4 pi r square delta r. Okay. That is the change in mass. Okay. So, the conservation condition is the same as we had used earlier. Change in mass in differential volume is equal to mass in minus mass out plus production. Okay, production within that differential volume. Okay. So, this first term is the change in mass in that differential volume. Mass in, okay, is due to the flux entering this differential volume at r. Okay. Okay. It is going to be equal to the flux in the radial direction at r. Note that only the flux perpendicular to the surface increases the mass, the flux parallel to the surface does not. So, this J r is the component of the flux perpendicular to the surface in the r direction times the surface area 4 pi r square times the time interval. Flux as mass per unit area per unit time multiplied by area multiplied by time. Mass out is going to be equal to at r plus delta r. Flux out is at this outer surface. J r at r plus delta r is leaving. If J is in the radial direction, the flux is leaving at the surface at r plus delta r. Okay. So, this has to be multiplied by 4 pi into r plus the whole square into delta T. And finally, the production term is going to be equal to the production per unit volume per unit time into the volume into delta T. Okay, so, these are the different terms in the conservation condition. Substitute that into this conservation condition, okay, and I will get C at r T plus delta T minus C okay, into 4 pi r square delta r is equal to the flux in minus the flux out. Okay. So, this the flux in is equal to J r at at r into 4 pi r square minus j r r plus delta r to 4 pi into r plus delta r the whole square. The whole thing has to be multiplied by delta t. Okay, the whole thing has to be multiplied by delta t. Okay, plus the source term, which is s into 4 pi r square delta r into delta t. I divide throughout by 4 pi r square delta r delta t. Okay. These factors of 4 pi will cancel out on all sides. Okay. And I will get c at r t plus delta t minus c at r t by delta t. Okay. Is equal to 1 by r square delta r into j r at r times r square, 4 pi I have cancelled out, minus j r at r plus delta r into r plus delta r the whole square. Okay. Plus s, of course, because I have divided throughout by the volume divided throughout by time. Okay. This thing here, it is the derivative of j r times r square with a negative sign. Okay. So, now that I have got this difference equation, I have to divide throughout by take the limit of delta t going to 0 and delta r going to 0. Okay. On the left side, I will just get partial c by partial t. Okay, on the left side, I will just get partial c by partial t. On the right side, I have 1 over r square into this difference divided by delta r. Okay. Quantity at r minus quantity at r plus delta r divided by delta r. It is the negative of the derivative, okay, because derivative is quantity at r plus delta r minus quantity at r divided by delta r. So, this is the negative of the derivative. Okay. So, I can write this as minus 1 by r square partial by partial r of r square j r plus s, where j r is the flux. Okay. So, this is the concentration equation except in, expressed in terms of the flux. Okay. Okay. And to get it in terms of the concentration field, I have to use Fick's law for diffusion. Okay. J r is equal to minus d partial c by partial r. Okay. Fick's law for diffusion. And then I will get partial c by partial t is equal to minus 1 over r square. Sorry, this has a plus sign, because minus times minus will give me plus 1 over r square d by dr of r square partial c by partial r plus s. I missed out a diffusion coefficient here. Okay, so, let me put that. Diffusion coefficient times r square times partial c by partial r plus s. Okay. And if constant diffusivity, you get partial c by partial t is equal to d by r square plus s. So, this is the mass conservation equation in a spherical coordinate system. Okay. Note that I have these terms r square here. Okay. Note that I have these terms r square here. Okay, 1 over r square d by dr of r square j r. Reason for that is surface area varies as a function of position. Surface area is increasing as the square of the radius, and because of that you have this r square in a spherical coordinate system. Okay. To compare, in a cylindrical, if you recall, the equivalent equation was partial c by partial t is equal to minus 1 over r plus s. Okay. This was in a cylindrical coordinate system. Okay. That was because there the surface area was increasing proportional to r. Contrast Cartesian coordinate system, the surface area was a constant, and therefore I got partial c by partial t is equal to minus partial jz by partial z plus s. Okay. So, these additional terms in the differential operator, the spatial differential operator, arise in curvilinear coordinate systems because the surface area is changing as the coordinate changes. Okay. You will have 1 over r d by dr of r times jr for a cylindrical coordinate system, and 1 over r square d by dr of r square gr for a spherical coordinate system. Okay, so you can get equivalent relations for the temperature. Okay, so for the energy balance, it will be rho Cp partial T by partial T is equal to minus 1 over r square d by dr of r square qr plus Se. Qr is equal to minus k partial T by partial r, which will give me the equation rho Cp partial T by partial T is equal to plus the energy source. If rho and Cp are a constant, then I can divide throughout by rho Cp. This term disappears, and here I will have Se by rho Cp, and here it will be the thermal diffusivity alpha. Okay. And if the thermal diffusivity is a constant, then the equation reduces to partial T by partial T is equal to 1 by alpha. So, this is the balance equation. Okay. So, we will start to get solutions of this balance equation, first for conduction into an infinite medium, and then we will examine conduction between two spherical surfaces. Okay. So, first problem, sphere of radius r. Okay, T is equal to T naught on the surface, T is equal to T infinity far away. Okay. What is the Nusselt number correlation for this? Okay. So, the procedure for evaluating this correlation, solve the differential equation at steady state in order to determine the temperature as a function of position. From that get the heat flux, okay. And from the heat flux you calculate what is the heat flux at the surface, the average flux, and divide that by k delta T by the diameter to get the Nusselt number correlation. Okay. So, this is at steady state. Okay, so the temperature far away as at steady state. Okay. Temperature is equal to T naught at r is equal to r, T is equal to T infinity for r going to infinity. Okay, and you have to solve the equation in order to get what is the variation of temperature. At steady state, in the absence of sources and sinks, the equation is 1 by r square d by dr of r square partial t by partial r is equal to 0. Okay. At steady state, partial t by partial t equal to 0, and at steady and in the absence of sources or sinks, S E equal to 0. You can solve this equation. Partial by partial r of r square partial t by partial r is equal to 0. R square partial t by partial r is equal to a constant. I will call it as minus a. Okay. It is any constant, a can be positive or negative. I am just naming it as minus a for convenience. Partial t by partial r is equal to minus a by r square plus b. Sorry, minus a by r square. Okay, and t is equal to a by r plus b. Integral of 1 over r square is minus 1 over r. Okay. So, that is the equation. Okay. As now we have to calculate the constants a and b. Okay. We have to calculate the constants a and b from the boundary conditions. Okay. As r goes to infinity, t is equal to t naught. Okay. As r goes to infinity, this first term goes to 0 because it is a divided by r, and as r goes to infinity, this first term is equal to 0. Okay. And this implies that b is equal to t naught. Sorry, my apologies. I had labeled T infinity as the temperature far. Okay, so I should use that same notation. T infinity is the temperature far from the object. Okay, so as r goes to infinity, T is equal to T infinity. Okay, and the equation becomes T minus T infinity is equal to A by r. T is equal to T naught. Okay, which implies that A is equal to r into T naught minus T infinity. Okay. So, the equation that I get for the temperature is T minus T infinity by T naught minus T infinity is equal to r by r. As r goes to infinity, T is equal to T infinity, and at r is equal to 0, T is equal to T naught. You can write this in compact form by defining it in terms of scaled variables. Okay. If we define r star is equal to r by r, okay, and T star is equal to T minus T infinity by T naught minus T infinity. Okay. Then the equation just becomes T star is equal to 1 by r star with conditions T star is equal to 0 for r star going to infinity and T star is equal to 1 at r star is equal to 1. Okay. So, these are the solutions. Okay. Now, what is the heat flux? Okay. Q r is equal to minus k partial T by partial r. Okay. I can express it in terms of T star. Okay. Express it in terms of T star minus k into T naught minus T infinity divided by r partial T star by partial r star. The heat flux at r star is equal to 1 is equal to minus k into T naught minus T infinity by r into partial by partial r star of 1 over r star. Okay. Partial by partial r of 1 over r is minus 1 over r square, and at r is equal to 1, that is equal to minus 1. Okay. The derivative of 1 over r is minus 1 over r square. Minus 1 over r square at r star is equal to 1 is just equal to minus 1. Okay. So, this just becomes equal to k into T naught minus T infinity by r. This is the flux at the surface. It is independent of position on the surface. Okay. It is independent of position on the surface. That means that the average flux is also equal to the same. Okay. Nusselt number is the flux by k into T naught minus T infinity by d. Note that the characteristic length for defining the Nusselt number for spherical particle is the diameter, not the radius. Okay. So, if I define it based upon that, this just becomes equal to k into T naught minus T infinity by r into d by k into T naught minus T infinity. This is equal to 2. This is the expression that we had derived, we had presented earlier for Nusselt number in the limit of low Peclet number. Diffusion dominated Nusselt number is equal to 2. That is the correlation. This is the derivation of that particular correlation. So, I will continue this in the next lecture, spherical coordinate system. First, we will look at this conduction from a sphere, and then we will look at conduction from a spherical shell. I will continue this in the next lecture. I will see you then.